In video number 2, I built 3 meshtastic nodes and used 2 of them on the 3rd and 4th videos to build 2 office mesh nodes. But now I'm going to work on the 3rd external one that uses solar power to make it into a 3rd external node that fetches GPS data and sends them through LoRa radio frequencies to the office nodes. Starting with obtaining the cheapest GPS receiver found online. Once it arrived, I noticed that it has no pins glued to it, so I had to do it manually. The tip of the soldering iron is previously used to melt plastic, so I'm not using it at the moment. Added to that, it doesn't heat properly enough to do solder with it, so I use another tip to do the work. After that, I made sure that these pins don't connect together, so I isolated them and glued. Now connecting the module. I connected the module to an Arduino just for testing. The original board for the mesh node is the ESP32, of course, but it won't show me the GPS module working or not in real time. As you can see in the monitor, it calls for NMEA data, but no answer, which it displays with commas. The first step before getting latitude and longitude data is to set up a satellite fix, which is necessary for the module to start working. All we have to do is place it outside for some time, roughly an hour or less. I found it online that is 20 minutes, but I like to confirm that it gets its fix once and for all. Once it gets its fix, it will display the latitude and longitude data on the screen like it shows here. It's not clear enough due to the baud rate, but that's fine as long as it's testing. Now going back to the meshtastic node with a working GPS module and connecting it to the board, to avoid the ESP32 misbehaving, you might want to power it externally, which is essential for a project that works for the longer term. Using the maximum current a board can tolerate can cause the board to shut down after a few times of using it. Here are some details I found on the Arduino Discord server that might help. Wireless Adafruit OLED. This is exactly what I'm using currently, so I'm not going to risk it and power them all at once. This guide recommends using a logic level shifter module, but I'll just power my GPS externally because I already have a solution to that. So we've got this 2500 milliamp hour battery and a 3.7 volt solar panel. Not exactly a powerhouse on its own, but with a bit of clever management, it'll absolutely keep that ESP32, LoRa module, OLED, and GPS running smoothly. The magic here is using meshtastic sleep modes and duty cycling to keep the power drain down. Without those power saving tricks, it's like leaving all the lights on 24/7. Totally not efficient. Alright, let's break it down. ESP32 can sit power down to its super low level when it's idle, and the other components like the LoRa module, OLED, and GPS all have their own quirks. The LoRa module is pretty chill when it's not transmitting, and the OLED just needs a bit of brightness control. The GPS, well, it's the hungry one, especially when it's locking onto satellites, but once it's got a fix, you can let it nap a bit. Now, runtime-wise, if you keep that power draw around 100 to 150 milliamps on average, you're looking at a solid day or more of runtime. Throw in that sunshine, and that little solar panel will top you off with enough juice to keep things rolling. Just let that node cache some rays. Bottom line, yes, it's totally doable. Just keep an eye on power saving feature, maybe beef up the battery if you want that multi-day autonomy, and you're golden. Let's keep it going. After setting up that power supply and hooking it to the mesh node, I took it outside for a test run under a clear sky. And guess what? Bingo. Crystal clear. Got about 6 or 7 satellites hanging overhead, all playing nice with the meshtastic node. Now let's break down how the whole tracking thing goes. Each satellite basically throws down a circle of where your device could be. When those circles overlap, boom, you've got yourself a real-time location. Bottom line, snag at least 3 to 4 satellites for a nice clear fix. To test the behavior of my 2 meshtastic office nodes, I configured my GPS node to send data each 20 seconds, and I set up another 2 mesh nodes. Each of them sends packets to get the location of the 3rd node. The first office node, attached to a phone by Bluetooth to the mesh app, gets to connect first and sends a request. Then the 2nd node, attached to a PC via serial, is opened after some time and sends a request each 10 seconds for 5 ties. Then we close the desktop node and keep the first one attached to the phone running. What happens? The first Office node gets the first data, then stops for some time. When the second Office node gets an answer, then timeouts. The second one then gets a third, timeouts a fourth, and then shuts down. Then the first Office node finally gets the last packet after a prolonged period. Second Office node, desktop via serial. When it joins, it also begins sending requests every 10 seconds. Because the mesh is shared, the third node responds to these requests. While the desktop node is active, the phone node's requests are effectively delayed or deprioritized, since the third node is busy responding to the desktop node's repeated queries. For the timeouts and shutdown, the desktop node sends 5 requests, gets 3 responses, then is shut down. During this period, the phone node experiences pauses in receiving data because the responses are directed to the desktop node. Alright, after the desktop node is closed, the phone node resumes receiving data, but only after a prolonged interval, since the mesh routing and request cycle had been disrupted by the desktop node's activity. The phone node's requests were effectively crowded out, not because the mesh gave priority, but because the desktop node's traffic dominated the request cycle. The phone node was sending requests at its default slower interval around 2 minutes. I configured my GPS node every 20 seconds to limit the power consumption when transmitting, and not to flood the mesh with packets. A 20-second cycle is often chosen as a compromise. It keeps updates fresh enough to follow movement in near real time, while still allowing the node to spend most of its time in low power. This interval also reduces congestion in the mesh to let multiple nodes coexist without overwhelming the limited bandwidth. As you can see on the phone, the nodes are overlapping because they're all in the exact same position. Now let's talk a bit about takeaways. In meshtastic nodes, GPS position data often appears inaccurate because low-cost modules and obstructed antenna placement can cause drift or fall back to the last known fix, making it seem like you're located somewhere you're not. I set up the office's node's location as fixed on the same latitude and longitude I received from the GPS node to demonstrate the overlapping with the GPS one. Secondly, the mesh channel itself is public, meaning anyone nearby can join and transmit. If one node floods the channel with excessive packets, it consumes airtime and interferes with others, which is why the ignore option exists to filter out noisy neighbors. And most critically, low-res limited bandwidth forces the firmware to send position updates to only one recipient at a time, rather than broadcasting to all nodes simultaneously. A deliberate design choice to conserve power and keep the mesh lightweight, though it restricts how widely position data can be shared in a single transmission.